This is our lecture on the basics of linear regression in R. I am going to cover some of the basic commands in R that you'll need to run least squares regression, but this particular lecture is not going to discuss heteroscedasticity, clustering, autocorrelation, or causality, all of which are interesting, but most of which will be covered in future lectures. There's plenty of time later on. We're going to use a few different packages in this lecture, among them janitor, broom, and car. Those are the new ones that you're going to need to install. So if you haven't done so yet, please pause the video now and install those packages. Today we're going to work with a very simple data set that contains some information on kids' test scores. So in particular, it contains a test score for the child at age 3. It includes the age of the child's mother when the child was born, information about the mom's educational status, and also a test score for the mother. If you're kind of rusty on interpreting interactions in a simple linear regression model, that's okay, but before you watch the rest of the video, you may want to click on this link down below. If you click on that link, you'll be taken to a document from my undergrad course I used to teach many years ago at Penn, and this document will walk you through lots of little examples with this particular data set, which I have borrowed from Andrew Gelman. Okay, so here is the data set. You can, first of all, load the data set from my website. So there is a command here in line 2 of the code block on the slide, kids gets read_CSV. Then there is a URL which takes you to my website and the data directory where you can download the dataset. So we're going to talk more about this read_CSV command in a future lecture, but for now, you can just take that command as given. If you run that command and then you type the word kids into the console, you will see the following dataset. So kids is a tibble, and it contains these columns that I mentioned before, and you can see that it has a total of 434 rows. Each row corresponds to a kid and has information about that kid's mom as well as the kid. All right, so let's start off with something simple. The column names in that tibble that we just looked at have dots in them. And we know that in the Tidyverse style guide, it is preferable to have underscores rather than dots. So the first thing that I'd like to do is clean up those names. Now, in many cases, when you're reading data from some source, there might be all kinds of funny issues in the column names, like embedded spaces, weird characters. And of course, you can clean these up manually by using some features from dplyr, but it's nice to have simple shortcuts for doing common tasks. And one of those shortcuts is the function clean_names from the R package called janitor. And this function is actually going to clean up the names of all of these columns in a really nice way. It's really simple. It's replacing those dots with underscores, makes life very, very simple. So kids gets clean name kids will overwrite the original kids data set and clean up the column names. And of course, you could do this manually. If you were going to use, if you were going to do that manually using dplyr, you could rename the columns one by one using the command rename. In R, the command for linear regression is LM, which stands for linear model. This command can be used to solve ordinary and weighted least squares problems. The syntax is as follows. LM, parentheses, something, and that something is going to be a formula, comma, and then a data frame. So first we say what's the form of the regression, and then we say what is the data that we're going to use for it. And where it says data frame, you can, of course, put in a tibble, because a tibble is just a data frame with some extra bells and whistles, as we learned in our lecture on basics of dplyr. Now, formula, that's a little bit more complicated. So there is something called our formula syntax, and I think I mentioned in our lecture about ggplot that the tilde was going to make another appearance and things would all become a bit clearer. Well, it has appeared, but perhaps they're not so clear yet. They will be soon. The first thing you need to know about formula syntax is that a tilde is used to separate the left-hand side from the right-hand side. So if you think about a regression with a y variable, an outcome you're trying to predict, that thing is going to go to the left of the tilde. And if you have an x variable, that's going to go to the right of the tilde. The plus, on the other hand, is used to separate right-hand side variables. So if we have two predictors, x1 and x2, that are appearing to the right of the tilde, we're going to have a plus between them. There will be more details on formula syntax later in this lecture. Okay, now that we know the lm command, we can use it to run a regression that predicts kid's score. So I'm going to take the kid's score and the mom's score, and I'm going to try to use the mom's score to predict the kid's score. So to do that, I will regress kid's score on MomIQ and an intercept, which I can do with this command. lm, parentheses, kid's score, tilde, MomIQ, comma, kids. So there I've specified the formula, and I've also specified the data frame where R should look to find the variables that are named in that formula. If I run that command, here's what I will get. R prints out call lm formula equals, and it shows us exactly what command we just ran. Then it shows us these results, coefficients. It gives me the intercept of about 25.8, and then it tells me the coefficient on MomIQ. We could also add another right-hand side predictor. So to do that, we need to separate it from MomIQ with a plus sign. That's what I do in the second code chunk on this slide. So now we have lm of kidscore underscore MomIQ plus momage, comma kids. And now we are predicting the kid's score using two different predictors from the kid's data frame. And again, if I run this command, R is going to print out the coefficients, and now it's going to give me the intercept as well of the coefficients on each of the two predictors. We may also want to plot the regression line. So let's go back to the simple regression that only regresses the kid's score on the mom's score. We can easily do this using ggplot. So I am going to pipe kids into ggplot, and I'm going to start making a scatter plot using geom_point, just as we learned in our lecture on ggplot basics. Then I'm going to add something new. The new thing appears in line 4. Lines 5 and 6 are just adding labels to the plot, as you should always do whenever you make a plot. So let's go back to line 4. I have a new geom for you. It is geom_smooth. And this geom is used to add various kinds of regression smoothers to a plot. It needs you to specify a method. So what I'm going to do here is I'm going to specify method equals lm. So that tells ggplot that I want you to add this smoother, and I want you to use a linear regression, in other words, linear model, to do the smoother. If you don't tell it anything else, now, of course, to run a regression, you need a formula. You need to know what the model is. But if you don't specify one, then what geom_smooth is going to do is it's going to default to regressing y on x. And how does it know what's y and what's x? Well, that's the great thing about an aesthetic mapping. It specifies that right off the bat. So in line 2, we've already said that the mom's score is on the x-axis and the kid's score is on the y-axis. So what will happen here is that ggplot will plot the regression line, and geom_smooth after geom_point is showing us both the points and the lines, along with some confidence bands for the regression line. So it's nice, it's easy, and we can see that indeed kid's score and mom's score are positively related, positively associated. Now, thus far, I have shown you the results of running a command, lm, with a model and a data frame. But that only showed us the coefficient estimates. What if we want to get all kinds of other goodies that often appear in regression tables? Well, we can get them. And to see how, the first block, I should say the only block of code on this slide, assigns the result of our linear regression command to a variable, which I'll call reg1 for regression number 1, because you guessed it, there's going to be many more regressions in this lecture. When I run line 1, nothing will happen, or what I should say is nothing will be displayed. So R has done a bunch of work and has stored the results of that work, but it hasn't printed anything out. However, to see that there's actually quite a lot of information inside of this reg1, we can use our favorite command, stir, which we encountered in our first lecture on base R programming. Remember that stir shows us what's inside of any R object. So what's inside of Reg 1? Well, Reg 1 is a list. And if you remember what a list is, it's the most versatile and flexible of all our data structures. Lists can contain anything, including other lists. So we see that Reg 1 is a list of 12 things, and those things are named. So we've got coefficients, and oh wow, the coefficients have attributes. What attributes do they have? Names. Okay, now you see why we had to spend all that time on base R, so that you would know what these things are. We've also got something that says QR, and oh, that's a list that seems to be a list of other things. So this is quite a lot of complex structure. But everything that you could ever hope for in a linear regression is contained inside this list. We just have to find a nice way to get the information that we want out. So, first of all, we can extract the coefficients. Now, I know I already showed you how to print the coefficients out, but those were printed out alongside that duplication of the original command that we used to run the regression. So if you just want the coefficients themselves, you can use the command coef. Coef of reg 1, where reg 1 is the result of running some regression with LM, is going to pull out the vector of coefficients, and it's a named vector. So you can see there the intercept and also the coefficient on the mom's score. We can also pull out the residuals with the command resid. You can also write out the whole word residuals if you want. So you just need to type resid of reg 1. Now, I have typed something extra there. I've put brackets 1 to 14. That's because there's a large number of residuals. There's over 400, and they would fill up the whole slide. So I'm just showing you the first 14 of them, but you can ignore those brackets in the 1 to 14. So that's how you can get the residuals out. You can also extract the fitted values. So those are like the y-hats. They're not like the y-hats. They are, in fact, the y-hats. To do that, you use the command fitted.values. And once again, there's hundreds of these, and I'm only going to display the first 14, so they fit on the slide. You don't need those brackets. You just need fitted.values, parentheses, reg 1. And now it's time for a lengthy exercise. This one may take you a while. So please pause the video and try your hand at these exercises. When you're done, make sure to check your results against the solutions on the course website. So, we've learned how to extract the coefficients, the residuals, and the fitted values, but what about standard errors and things like that? Or maybe even an R-squared? Well, we can easily view these by using the command summary. If we use the command summary with a regression object, so the output from some LM command, we will get this table with lots and lots of information. We've got the coefficient estimates, we've got standard errors, we have t-statistics, we even have p-values for the test of a null hypothesis that the given coefficient is 0, along with the much maligned significance stars. We've also got the R-squared. We've got the adjusted R-squared, if you're familiar with that. We have the F statistic for a test of the joint hypothesis that the coefficients on all of the predictors are 0. And we've even got the residual standard error. So there's a lot of information here. And this is getting closer to the sort of thing that we might actually want to report when we run a regression. Although we will say a little bit more about how to make this look prettier, because right now it's very like 1982. It's the kind of thing that you might see coming out of the IBM PC Junior, running Microsoft DOS. So we're going to want to do something a little bit fancier than this and make a nicer table, but this is definitely a start. One thing you just need to be aware of is that by default, when you run a linear regression in R, all the standard error calculations, and that would of course include the p-values, assumes IID homoscedastic normal errors. Now, we may want to relax the homoscedasticity assumption. We're going to talk about that in a future lecture. The consequence of assuming normal errors is that the p-values are calculated using the t-distribution. So they're calculated using the finite sampling distribution under normality rather than the asymptotic distribution. The only real upshot of that is that they're going to be slightly more conservative than the p-values that you would get if you were relying on the asymptotic approximation using the central limit theory. So basically, that's not a big deal, but we may perhaps not be happy about the homoscedastic error assumption that's being made for the standard errors, but we've got to crawl before we can walk and walk before we can run. So for today, we're just going to ignore that issue, and we're going to look at the default inferences that R produces for us. Now, what about summary? Well, summary of Reg 1 also produces a gigantic object. What kind of object is it? Well, we can find out using our handy stir command. It's a list. You're starting to get the hang of it now. Lists are going to be what's used in R to contain any sort of complex list of heterogeneous things. So summary of Reg 1 is itself a list, but summary of Reg 1 is yet another list. It's a list that contains all kinds of things, and we can see that they're all in here. There's some confusing things. There's some easier to understand things. The coefficients are down there. But really, this is a kind of a mess. So if we want to produce a better table of output than the one we saw on the last slide, we may not want to start from directly interrogating the list elements that we see inside of this summary. So we could use this command to extract things, like if I told you, hey, there's a list element inside of summary called r.squared, well, you could then use that to extract the r squared as follows, using the $ notation that we learned in our lecture on base R that's used to extract list elements by name. And we could get out the fstat that way, and we could get out the p-values, but it's a pain. We would need to know all the names. We would need to know all the positions. And fortunately, there's a better way, namely the Broom package from the Tidy Models suite of ML packages. So we're going to use this package Broom, and here's how it works. If you haven't already installed Broom, make sure that you do that now, and then run library Broom, and follow that by tidy reg 1. What does that do? Well, it provides much of the same information that that we got from our summarize command, rather our summary command on this previous slide. So you can see things like standard errors and p-values and so on. Except that now, with Broom and the tidy command, this is producing a nice tidy tibble that we can easily manipulate subsequently. So this is a lot easier because we can extract whatever we want from this by using dplyr or even just base R commands. So we see we've got the names of the different coefficients there, intercept and also the MOMIQ. We have the estimates, we have the standard errors, we have the t-statistic, and we have the p-value for the test of the null hypothesis that that coefficient is 0. If we want to get things like the r squared and the residual standard deviation, we can do that too. We will use the glance command also from Broom. So tidy is going to give us the basic regression output, so estimates and standard errors, and glance is going to give us the summaries of the model fit. So that includes the r squared, that includes things like AIC and BIC, that includes the f statistic, and so on. The nice thing about Broom is that it plays nicely with dplyr because it returns tidy tibbles. So for example, if I wanted to extract the p-value for the test of the null hypothesis that the coefficient on the mom's test score is 0, I could do so with this tidy pipeline. Another very, very helpful command from Broom is called augment. This command can be used to connect the results of a regression with some useful things that rather, I should say, this command can be used to connect the data set that was used to run a regression with some useful outputs from that regression. So in particular, if you run the command augment reg1, kids, what will happen is that R will return the original data set that was used to run reg1. I should say, I misspoke. What's happening here is that we are, apologies for the mistake. What's happening here is that if you say augment reg1, kids, R will augment the tibble kids with some information from the regression reg1. Now, it happens to be the case that kids is the data set we used to run reg1, so this all makes sense. So in particular, what we're going to have when we're all done is some additional columns. So if you look at the output on the first block of this slide, you'll see that we have the 4 columns from the kids data frame kid score, mom HS, and so on. But then we have some additional columns, dot fitted, dot resid, and so on. These first two columns among those ones that begin with a dot are the fitted values and the residuals from the regression. If you want to know some more about what this augment command is doing, or what tidy is doing, or what glance is doing, you should take a look at the R help files. In particular, you should look at the help file for tidy.lm, glance.lm, and augment.lm. This is foreshadowing something that's going to come later. These commands, tidy, glance, and augment, are quite general. They can be used with lots of different models, not just linear regression models. So to find the help file that is specifically about using tidy, glance, and augment with linear regression, you need to look up these commands tidy.lm, glance.lm, and so on. And now it's time for one more exercise. As usual, pause the video, take a few minutes, and then compare your results to those on the course website.